Hello everybody. So today I will talk about the system design of Dropbox. So I will do the deep dives in this video. So my topics will be this one: resumable upload and download, and durability of the files, and scalability of the system. And that being said, I'd like to begin with a quick review of the high-level design. So in a system, what we'd like to achieve is the automatic syncing of the file between the local machine of the users and the remote server. So user should be able to upload a file, user can download the file, and these downloading and uploading should be automatically done in the background process of the local machine. And we store the files in the S3, and so we store the file metadata in a database, PostgreSQL, and the file content itself in the blob storage, S3. And we talked about, these APIs. The most interesting thing is, I believe, get updated files. So in the local agent, he has to know which files are newly updated or added in the remote machine. So periodically, like every 1 minute, the local agent makes a request to, get updated files API and gets the list of files, and then it downloads the latest file from S3. So that's the high level design. And that being said, I will start the deep dives. Okay, so I will start with the resumable upload and download. So I'd like to realize this because we specified fault tolerance in the non-function requirement. So let's say user would like to upload a big file, like 50 gigabyte of file. And after the file is uploaded, after 49 kilobytes of the file has been uploaded, let's say there is a kind of network disruption and the uploading failed. In that case, I don't want a user to upload from scratch. I want the user to upload only the remaining 1 gigabyte, because if he begins from scratch, it takes more time, and also it wastes the network resource. So I don't want to do it. So that being said, to avoid that, we can use the resumable upload. So actually, we use S3 upload, and S3 natively supports the resumable upload. So, and actually, this is done automatically internally inside of AWS SDK. So if we hit S3's raw API, we have to take care of the resumable upload, or I should say multi-part upload. But as long as we use the S3 SDK, like TypeScript or JavaScript SDK, we actually don't have to take care of the multi-part upload, implementation. So what I will talk from now is all about the internal mechanism of AWS SDK and how it achieves it. So basically, internally, SDK splits the big file into smaller pieces. Typically, when the file size is more than 100 megabytes, it splits the pieces of 5 megabytes. Yeah, and it uploads the file. And there is a kind of, S3 in the server side tracks every piece, and then when all the files all the chunks are uploaded, S3 now merges them together back to the original file. So that's how it works. So that being said, I have a few points I'd like to talk maybe about the details of the, behavior. So number one, how S3 can know all the files are uploaded. So There is a okay. The answer is that in S3 there is a kind of API which is hit when all the chunks are uploaded by the client. So this one is called, I forgot the name. Let me check. Yep, complete multi-part upload API. So when the client uploads all the chunks, when they finish, the client should also hit multi-part upload. So sorry, complete multi-part upload API. And that's the kind of signal to the server side that all the chunks are uploaded. Okay, and second thing I'd like to mention is how S3 can know the kind of file corruption which occurs in the process of uploading. The answer is it uses a checksum. So before uploading the chunk into the server side, the client side calculates the checksum of the file and add it to the file chunk. And in the server side calculates the checksum of the original file on himself. Then they validate that it's the same as the checksum calculated in the front end, or it's just the client side. So that's how S3 can detect the file corruption. And I have two more things I'd like to mention. So okay, the one more thing is how the client side can resume the upload when after there is a kind of disruption. So S3 has the kind of least part API. So when client side like to resume the multi-part upload from the last time it failed, it hit least part API. Let me check quickly. Yeah, least part API, and then it checks which parts are not uploaded yet, and now client side can upload only the parts which has not been uploaded, which has not been completed. So that's the thing. And the last one more thing I'd like to mention. So what happens if the file upload fails and client never resumes? So let's say there is a user who'd like to upload the file and he uploaded maybe 90% of the file, but he changed my mind and stopped uploading. In that case, in S3, the parts of the file are remaining. It becomes a zombie files. And it costs money actually. So something I can do is we set the kind of life cycle of the file, and we can specify like if the file is not uploaded for 1 week, we delete all the file chunks uncompleted. So that's something I can do. Of course, we can add a kind of cron job which delete all the remaining zombie files chunks, but instead of that, we can use the S3 lifecycle. Okay, so that's about the resumable upload. So for resumable download, the same thing can be said. When user tries to download the file, big file, if it finishes 99% and then it fails, the user should be able to download only the remaining 1%. For that, client should specify which part of the file he'd like to download from the original whole file. So we can, and this mechanism comes with AWS SDK, just like the multi-part upload. So actually, as long as we use the AWS SDK, we don't have to take care of it. But internally, what it does is it specifies the kind of file range. It uses the range header of HTTP. So it specifies like, hey, I'd like to get from 0 GB until the offset 1 GB. Oh, it's too big. From offset 0 GB to 100 MB. Oh, sorry, it's still big. Okay, like I'd like to get from 0 MB to 5 MB, or maybe client specifies 10 MB to 15 MB, and fetches only that range of the file. And now client side merges them together after all the parts are downloaded. And of course, for these uploads and downloads, the client side can do concurrent upload or concurrent download. So yeah, that's something I'd like to mention about resumable upload and download. Okay, so now I will talk about the durability. So durability, especially about the file, because file is the exactly what is most important in terms of the business of the as a product of Dropbox. So the file content is stored in S3, and S3 originally has natively provides a very high durability, which is called 11.9. So this is it. So Amazon S3 is designed for 11.9 durability. Yeah. So maybe out of 1 trillion files, maybe one of them may be lost. So that's the kind of 11.9. And we can guarantee higher durability by doing the multi availability zone redundancy. So this means that if we specify that S3 duplicates the file to multiple availability zones, like US East 1 and also US East 2. So each availability zone corresponds to one data center. So even if one data center goes down and the file is broken because of, let's say, natural disaster, there is another data center which should be working, so the file is durable all the more. So that's about the S3 durability. Okay, and for the file metadata, I will mention this too. So we can use a kind of backup, which is as the snapshot as S3, or we can do a kind of read replica. So read replica can be used not only availability but also for the durability, because we put the read replica in multi across availability zones. It means that in the same theory which I mentioned, the file, even if one file in availability zone is broken, there is another one in the even if one database in one availability zone is broken, there is another one in another availability zone. So that's the durability of PostgreSQL data. Now I will talk about the most interesting thing, maybe scalability. So scalability, 100 million daily active users and 50 gigabyte per file. So I will copy this number and do the back of the envelope estimation calculation. So I'd like to talk about the scalability. I'd like to discuss the scalability from two perspectives. Number one is the throughput, and number two is the file size. So for the throughput, so there are 100 million daily active users. So daily active users here is a kind of tricky, because even if the user is not active, the file should be synced to the local machine. But I will assume that this daily active users, 100 million, this is exactly the number of devices which should be synced on a daily basis, or I should say all the time. So that being said, we provided these APIs: create file metadata, upload file, get file metadata, get download file, get updated files. So something I can say is, this is obviously the read heavy. because if user uploads one file, it should be downloaded by multiple users in the same group. So especially read heavy. So I will, in this discussion, I will talk only specifically about the download API. So maybe upload API, like create file metadata. This can be a little bit heavy loaded because this is a write request rather than read request. But number of requests throughput is much higher in read request. So I'd like to talk about read request throughput from here. And that being said, we can find two parts, S3 and main DB. So for S3, I don't discuss so much about this here because S3 infinitely scales internally because S3 uses a consistent hashing to horizontally scale the internal servers. And so the thing is, if the file I upload from my client and the file which is uploaded from another client, in most cases, they are routed into different physical servers and handled there. Yeah, in most cases. Yeah, as a result of consistent hashing. So that's what I mean by infinitely scales. And so as long as the same file is called again and again, downloaded again and again, this wouldn't be the problem. Of course, it's the same file is downloaded again and again. I mean, because the requests are routed into the same physical node, it can be quite heavy for that node. Yeah, but in that case, we can use kind of CDN to cache the file in the edge location. So yeah, for S3, we don't have to take care of this too much. For PostgreSQL, okay, I will talk about two APIs, get file metadata, as I said, and get update files. This is the short polling API. So this is quite a big concern because short polling means every client hits the API again and again and again, which can load heavy, which can be heavy loaded for servers. So I will go with get file metadata. So there are 100 million interactive users, 50 gigabit per file. The most important thing is how many files are uploaded per day. Let's assume something here. Let's say there are 100 million users, so 10% of the user uploads on average one file per day. So there should be 1 million file per day. Maybe this is too small. Let's say half of the users, no, maybe 20% of the users upload 5 files a day. Because nowadays, the pictures, like images, which is taken in the smartphone can be synced. So in that case, there should be many files. So I will go with this. So there are 100 million files per day. And this number is fetched by every user. So this is the request per sec. 100 million files. Yeah. So this becomes 110 million billion. 10 billion requests per sec. Oh wait, so this is per day. So, okay, so this is equal to the 1K requests per sec, because 1 day is around 10 to the 5 seconds. Yeah. So 1K requests per sec. This is upload, and for read, this is 100 times, which means 100K requests per sec. Okay, good. So this is too, high to be handled by only a, single node of the PostgreSQL. Because in PostgreSQL, read queries typically, around 10K to 50K requests per sec of read query can be handled by one single node. So the solution is we use read replicas. So because each server can handle, each database replica can handle around 10K to 50K requests per sec. Maybe we need 10 to maybe 20. Maybe 10 to 2, 2 to 10. So maybe 10 replicas is good enough. Okay. Yeah, because we told that we are okay with eventual consistency, this read replicas completely works. Okay. And another API, get update files. So for this one, I said every 1 minute the request is made from the client. And let's say, each user on average has one device. So it should be 100 million device. And they make once every 60 seconds. So the request per sec is like this. So it should be around, 1 million requests per sec of read. So this is quite high, assuming that each read replica can handle 10K requests per sec. It need 100 read replicas. So but if we assume that each replica can handle 50K requests per sec, we need only 20. So 20 read replicas, this is completely possible. So I think I can use this. Yeah. So I will go with read replicas. And maybe we can use the caching with Redis. Let me think. Yeah, so kind of idea we can use is we use the cache, and in each cache we store the kind of use, let's say, the uploaded file in the specific 1 minute in specific folder workspace. We list the files file IDs which are updated in the duration in the Redis as the key value cache. That's another solution I think I can use. Yeah, I don't mention more about this, but it's another solution, I think. Okay, so that is about the throughput. Oh, and I forgot to mention, but I always forget to mention this, but of course, we also have to think of the other layers. Actually, the database layer is the biggest concern because it has the storage access, and storage access is very slow compared with other operations like memory saving or CPU, operations. So I talked about this first, but of course I have to talk about other layers. So for upload service, download service, sync service, all of the APIs supported in these in these services are stateless. So the request can be handled to any server in the same service. So here I can use the horizontal scale route. Yeah. So typically, each server can handle 1K requests per sec. So maybe we need like for upload, maybe for download here we need exactly one server. Yeah. But maybe for the availability perspective, maybe we need 2 or 3 servers scaling out. And for sync service, we need 1000 servers scaling out. And of course, if there is a kind of spike or something, we can auto scale servers with, let's say, AW auto scaling. Yeah, it scales the servers. I mean, it increases the number of servers according to the CPU memory usage, or maybe according to the number of traffics. Yeah, and for API gateway, I don't have to take care too much of this because this is internally the fleet of servers. So it internally scales out. So yeah, it's okay. Good. So now I talked about the scalability in terms of the throughput. Now I'd like to talk about the scalability from the storage. So we have to think of two things again. One is file content, the blob storage itself, and also file metadata. Yeah, file metadata, I'm pretty sure this is the biggest table in the main DB because file is uploaded every day, and for every file, new record is created. User, device, folder, it doesn't increase in that speed, in that rate. Okay, so for S3, we accept 50 gigabyte of file, but here, let's assume that each file is on average 1 megabyte, because it includes the, let's say, text file and also the pictures. So typically, one picture is around 2 to 5 megabytes, and text file is around maybe 1 kilobyte, 2 kilobyte, something. So on average, let's assume it 1 megabyte. So 1 megabyte file, and I calculate this number. So in a day, how big it is? So 100 million. This is 10 to the 6 and 10 to the 8. So this should be 10 to 14 byte. So this is kilobyte, megabyte, gigabyte, terabyte, 100 terabyte per day. Am I correct? Yeah. Yeah, this is the, oh yeah, because 1 megabyte is 10 to 6, so I have to update from mega to giga to tera. So yeah, 100 terabyte. So this is so big, but as I said, S3 internally auto scales. Sorry, infinitely scales internally. So actually, we don't have to take care too much about that. But of course, it costs a lot of money. So something I can tell is, oh, it's already written here. But if the file is very old and not accessed, or maybe I should say specific folder is not referenced that much anymore, maybe we can use the files, S3 files, into S3 Glacier, which is a cold storage. So for the files in the cold storage, it takes more time to download, but it costs much less. So that's the option for the cost efficiency of this system. Okay, so the remaining final piece is file metadata. 100 million files per day. So this is exactly the number of records of parameter data per day. And let's say each record has 100 bytes. So this becomes megabyte, gigabyte, 10 gigabyte per day. So in a year, it becomes, because 300 times, so 3 terabyte per day. Okay, so this is actually not so big. Oh no, sorry. Because nowadays, PostgreSQL, like AWS Aurora, can have 256 terabytes of data in the storage. So it takes around 80 years to store, run out of the storage. So this is fine with only one single node. So a single database. But if this is really with the scale, we can use the DB sharding. So we can shard according to the folder ID, because in a system, if the folder is different, each folder can be 100 independently. There is no kind of join query across folders. So yeah, if we'd like to scale more, we can use the sharding, DB sharding. Okay, so that's about the scalability. Good. That being said, okay, I finished my today's practice. Thank you so much. Bye.